So, let's go over what you need to know. The first homework on chapter 1 is due on Friday on WebAssign. The next homework on chapter 21 will be due on the 26th. And your first quiz on chapter 1 will be today in the SI session. You're allowed one sheet of notes. So I'm going to continue on with chapter 21. Why are you not? So we were talking about continental plates. And the boundaries between continental plates are some of the most geologically active places on the Earth. There are places where plates are rubbing against each other, moving into each other, moving apart. This causes lots of active geology. And the crust is made of two different types. There's continental crust, which forms the continents. It's primarily composed of silica-based minerals, which gives it a lower density than oceanic crust. It's a lot like, it's similar to granite as a rock, while oceanic crust is primarily composed of magnesium iron-rich basaltic rock, which is a denser rock, which gives it a higher density than continental crust. We'll go into what these types of rock are, but there's several terms for the types of rock involved. These are minerals with more silica, which makes them lower density. These are minerals with less silica, which makes them higher density. These are called felsic minerals. These are called mafic minerals. And there are three types of plate boundaries. Divergent plate boundaries, which are located along mid-ocean ridges, where two plates are moving apart. So along the mid-ocean ridge of the Atlantic, in Iceland, at the East African Rift Valley, these are all places where two plates are moving apart. There are convergent boundaries where two plates are driven together, where one plate gets consumed by the other. So most of the divergent boundaries are in the ocean. Convergent boundaries are things like the west coast of South America, forming the Andes, where the Pacific plate is going under the Andes. Along the eastern rim of the Pacific, like in Japan, where Pacific plate is going under the Eurasian plate, or where places like Indonesia, where the Indian Ocean plate is going under the plate that Indonesia is on, which I can't remember off the top of my head. And then there are transform boundaries. That's places where two plates are sliding side to side. And there you get earthquakes. So the San Andreas Fault in California, where the Pacific plate is moving one direction, the North American plate is moving the opposite direction, but it's along the direction of the fault. So they're sliding against each other. In Haiti, the Caribbean plate is sliding against, I think, the South American plate, but I'm not sure. It might be another small plate in that area. But there's a fault line through Haiti. That's a transform fault. That's why we've gotten those big earthquakes. So these plates, these continental plates, are made of what is called the lithosphere, which is the upper layer that is the crust and the rigid portion of the mantle below it. Below that, there is a higher temperature layer, which is softer and flows more easily. This is the asthenosphere. It's sort of basically solid, but sort of flows over very long time periods. It's sort of, where you can think of it as sort of soft and gooey. It's relatively plastic, it easily deforms. It's much more easily deformed than the lithosphere on top. And you can think of the lithosphere as basically floating on top of the asthenosphere. We see a lot of things that look like floating, like if the lithosphere is pushed down by something and then that thing that was pushing it down is suddenly released, like when glaciers melt. So when glaciers on top of the lithosphere, it weighs it down. And so it actually sinks down in the ionosphere, and when glaciers retreat, it floats back up. So there are places that are still rising up from the last glacial retreat. Because of what's called isostasis. But yeah, so you can generally think of the lithosphere as floating on top of the ionosphere. That's why these plates can move around. They're all floating on top of a more liquidy layer. And isostasis is the concept that the solid lithosphere floats in gravitational equilibrium on the plastic ionosphere. So this is like, if you put a block of wood in the water, it'll sink to a certain depth and be stable there at equilibrium. And if you push it down, when you pull your finger off, it'll bounce back up and settle back down. Same thing happens with the plates. So for example, the continental plates float higher because they're less dense than oceanic plates. And then they're also thicker. So they're both thicker and less dense. So they float higher up and they're wider. And in any given time, all of the plates are more or less in isostatic equilibrium. They're stable. Some places are still changing, but it's only a few places. So there's like the Hudson Bay area in Canada or something, these things rising. And mountain ranges represent thicker masses of continental material, and therefore they float higher up. They also penetrate further down as well. So when you have a mountain range, if you look at the top of the lithosphere, it's going up, but if you look at the bottom of the lithosphere, it's also dipping down. Like this. You see there's this root. You have the top up here, but you also have a root down here. Much like the way that less dense ice floats in water, less dense continental crust floats on the atmosphere. Name? Wires. Wires? Okay. All right. Now, the movement of these plates, the movement of the lithosphere, is due to forces within the ionosphere. So because the ionosphere is softer and more flowy, it can move over large time scales. So it's thought that movement within the ionosphere is caused by convection cells, where warmer spots in the magma rise up, cooler areas sink down, and that is what's driving the movement of the plates. There's debates about how big these cells are, whether there's a layer of convection cells closer to the surface of the Earth and then another layer below, and then they're driven by interactions with the core, or if they're really big cells going straight from the core up. But it's generally thought that they are convection cells. So there's some unequal temperature distribution within the ionosphere and upper mantle, which results in hot, less dense material rising up and cooler, more dense material sinking down. And this drags the plates along with it as it circulates. And so you have hot, deep material rising up at these diverging areas. And then as material sinks down, it melts. So that's the other place you get lots of volcanoes. So these are also helped along by the fact that the spreading ridges get pushed up by this rising hot magma, and the lithospheric plates penetrating into the ionosphere are sinking down and are pulled down by gravity. So the whole thing gets driven, it gets pushed along by these convection currents, but it's also assisted by gravity of these, the plates sort of sliding down. So drag from the more active lithosphere drives that outermost solid lithosphere. And it's slow, but steady and somewhat complicated. So let's talk about the different types of boundaries. So the divergent boundaries are where two plates are separating apart. The vast majority of these are in the ocean because if a divergent boundary lasts long enough, it separates enough far apart to flood with water, basically. Divergent boundaries turn into oceans and seas. So the mid-ocean ridge system represents a zone where two plates are moving apart, a divergent boundary. What happens is initially molten magma gets shouldered up on either side of the rift, and that causes the lithospheric plates to slowly separate apart, and drag from the underlying lithosphere keeps those plates in motion. But along that mid-ocean ridge, there's constant volcanic activity because the crust is tearing apart and magma is coming up and turning into lava. Lava's coming out from the crack, basically. And that's making new seafloor. And when that process starts on land, it causes a rift valley, which eventually tears open and forms like a linear sea, like the Red Sea. And as it keeps going, it can form, separate the continents. So, as we talked about earlier, the Atlantic Ocean used to be not there. So the Atlantic Ocean used to not, North America, South America, and Africa all used to all be next to each other, and they tore apart. So what you get is oceanic crust separating in each direction, new magma coming out of along the rift in the middle, forming a ridge. And as it cools and settles down, it goes off in either direction. And that creates new crust. So divergent boundaries create new crust. So as a portion of the plate moves away from the hot spreading center, it cools, it contracts, it becomes more dense. And due to this increase in density going away from the spreading center, it gets denser, so it starts to sink down. The plate will gradually subside and the oceans will grow deeper. That's part of why we have a ridge at that point. So here's a video about the Mid-Atlantic Ridge. Or it should be. Oh, no, it just needed a moment to load.
But while some plates crash together, others tear apart. It happens under the ocean, like here, in the middle of the Atlantic. Lava erupts at the boundary between two crustal plates, sealing the tear. This is the Mid-Atlantic Ridge, a 10,000-mile tear on the floor of the Atlantic Ocean. The ridge is a line of underwater volcanoes, and it's here that new oceanic crust is formed. It stretches from the South Atlantic all the way to Iceland in the north, where it rises above sea level. From the air, the Mid-Atlantic Ridge is an awesome sight. This dramatic scar in the landscape marks the boundary between the North American crustal plate on the left side and the European plate on the right. The gap between ocean plates is filling in at a rate of an inch a year. Part of the restless movement of the Earth's crust that's reshaping our world.
So that's the Mid-Atlantic Ridge. And it does come above the water in Iceland. So that's part of why Iceland has so many so much volcanic activity. And also why electricity is so cheap there. Then the convergent boundary is where two plates are coming together. And there's basically three possible combinations. Because there's two types of plates, continental and oceanic. You can either have two of the same type come together or one of each come together. So the three combinations that are possible are oceanic-oceanic convergent boundaries, where oceanic plate runs into another oceanic plate, oceanic continent. So this would be like where the Marianas Trench is with Japan. Also similar to what's going on near Japan. The Marianas Trench, which is near the Marianas Islands, that's an oceanic-oceanic boundary. Oceanic continental convergent boundary, that occurs when oceanic crust runs into continental crust and subsides. So this would be like the west coast of South America where the Andes are. And then a continental-continental convergent boundary, this is where two big honking lumps of continental crust slam into each other and pile up. So the most active of these at the moment is the Himalayas, where the Indian subcontinent is slamming into Asia. So in the first two, oceanic-oceanic and oceanic-continental, when there is oceanic crust, one of the plates will subside underneath the other. The oceanic crust will end up going underneath the other plate in a process that's called subduction. So a subduction zone is where this is happening. At subduction zones, you get volcanoes because that plate melts as it sinks deeper into the mantle. You get earthquake. You can get earthquakes as the plates slide against each other. So this is a subduction zone. So if you have an oceanic-oceanic convergence, you have two plates that are roughly the same density. When they combine, one of them will go under the other. Usually it's the older one, which is likely to be slightly denser, and that's the one that sinks under the other one. But there can be other factors involved. When this happens, you tend to get long, narrow, deep sea trenches. The deepest spot in the ocean is one of these trenches, the Marianas Trench. And they mark the zone where one plate gets subducted under the other. And as that plate sinks deeper into the mantle, it gets heated up and starts to melt. That molten rock from that plate rises up above it, through the mantle and crust above it, and forms a volcanic island arc. So this is how you make new land in the oceans, volcanic islands. So all those volcanic islands rimming the Pacific Ocean, that's what's causing them. So there's strings of volcanic islands like that all over the place. So what you get is one plate sinks under the other, it melts, the molten material rises up and forms a volcanic island arc. So there's this deep sea trench and a volcanic island arc next to each other. And here's a video showing an example of this. This is the Marianas Islands and the Marianas Trench.
If we remove the ocean water around the islands, the collision is revealed on the sea floor.
Volcanic island.
The plates come together just east of the Mariana Islands. By looking beneath the seafloor, we have an even better view of the colliding plates. The collision formed a deep canyon near the islands. This is the Mariana Trench, which bottoms out at 36,200 feet below sea level, the lowest spot on Earth. Mount Everest would easily fit in the trench, with over a mile to spare before reaching sea level. Plate tectonics is driving the two plates together at the rate of a few inches per year. The plate on the right, which is the heavier of the two, is sinking below the lighter plate. This is called a subduction zone. As the plate sinks deeper, it melts. Magma is created, which can force its way up through the plate above. Volcanoes erupt on the seafloor. Eventually, they might become islands, like Pagan and Anatahan.
So, yeah, the deepest point in the oceans is in the Mariana Trench. It's called the Challenger Deep. And it's about 11,000 meters deep. Now, when oceanic crust meets continental crust, it's much easier to figure out what happens. Well, it's simpler. Continental crust is less dense than oceanic crust. Continental crust is around 2.7 grams per cubic meter. Oceanic crust is around 3 grams per cubic centimeter. So, since the continental crust is lighter, the oceanic crust is always the one that gets subducted. So what you'll get is continental crust on top, oceanic crust thrust underneath. A trench will develop along the zone where the oceanic crust is subducted. And as the oceanic crust descends towards the asthenosphere, it begins to melt. And magma will rise up and through the overriding continental plate, forming a volcanic mountain range. So some examples of this are the Andes along the west coast of South America, where the Pacific plate is going under the South American plate, and the Cascades up in Oregon and Washington, where the small plate near Oregon and Washington is going under the North American plate. I can never remember the name of that plate. But these create these volcanic mountain ranges on continents. And sort of weird example of something that happened oddly, the Rocky Mountains are a strange case that was caused by subsidence, where there were folding mountains created far away from where the actual subsidence occurred. So we'll watch a short video about how the Rocky Mountains formed. They're a little different. They're sort of in between this and the other next.
On our journey south along the Rocky Mountains, we're entering a very different landscape. From Montana southward, the Rockies are made from ancient granite, 1.7 billion years old. Granite makes up much of the deepest part of the continental crust. That's why geologists call this rock the basement. The Canadian Rockies are built from sedimentary rocks piled up on top of the continental foundations. So why does granite suddenly appear here in the American Rockies? But there's an even greater puzzle. Mountains usually form close to plate boundaries, but the Southern Rockies sit a long way from the plate margin. The Front Range in Colorado is 1,000 miles from where the Pacific and North American plates actually meet. Geologists have come up with an explanation. They believe that the subducting Pacific Ocean plate is responsible. Ocean crust had been pushed deep into the mantle beneath North America for 100 million years when something unusual happened. Plates started to subduct at a shallower angle. Instead of plummeting steeply, it sliced beneath North America horizontally. This change had dramatic consequences.
The big oceanic plate in the Pacific didn't go deep down, it went in shallow like a spatula under a pizza. So something happened 68 million years ago over in California. That plate drives under North America, but instead of diving deeply, it comes in shallow, and 1,000 miles away from the coast, up from the ground, sprout the Rocky Mountains.
For millions of years, the ocean plate scraped along the underside of North America. It created friction, breaking up the basement granite of the North American plate and punching it upward. Structural geologist Carl Karlstrom demonstrates.
Because it was at a shallower angle beneath North America, it was scraping along the base of North America. When that happens, it puts the plate under compression like this, because it's being both pushed at the end and scraped along at the bottom. So it squeezes, pushes up the mountains, and it transferred this mountain building from the edge to great distance from the plate margin.
The shallow angle trajectory of the Pacific Ocean plate explains why these mountains formed so far inland. And it also explains the presence of granite. Thrust up through layers of sedimentary rock, the broken granite became the Rocky Mountains of the South. Red Rocks Park, Denver, Colorado. A landscape forged by granite uplift. The granite mountains here have been pushed up 4 miles. On top of the granite lie spectacular red slabs of rock known as flat irons. They're the patchwork remains of sedimentary rock that once blanketed the entire granite basement. Kirk Johnson demonstrates how these granite peaks punched up through the layers of red rock around them.
I'm going to use my assistants, Veronica and Ian, to help me explain how the Rocky Mountains in Colorado formed. Imagine, if you will, that Veronica and Ian are composed of 1.7 billion year old metamorphic rocks, the basement rock of Colorado.
Before the mountains grew, layers of sedimentary rock covered the granite.
And then about 68 million years ago, the mountain where Ian is starts to break and lift up and move up. So you see the uplift forming. And what's happening is that layer of sediments being deformed and bent. And these are the flat irons at Red Rocks. As the mountain comes up, overlying sediments are eroded off and deposited into the adjacent basin. And eventually, Ian's granitic back is exposed as the core of the Rocky Mountains. Veronica remains deeply buried beneath Denver, still covered with deep sediments, and the sediments eroded off the uplifting Rocky Mountains.
That uplift created a bunch of interesting geological features like the Grand Canyon. Part of why the Grand Canyon is so impressive is because the Colorado River used to be a meandering river, and then the whole area rose up, and so it started wearing directly straight down. So you got a curvy river digging a canyon. So this is oceanic continental convergence. Generally, the oceanic crust sinks beneath, melts, and forms volcanic mountains on the continent. So this is basically what's happening in the Andes and the Cascades along the west coast of South America and northern US. If two continental plates run into each other, they're basically both too light and too thick to sink. They're both of relatively low density, and so there's minimal subduction. Usually what happens is there's some oceanic crust attached, that oceanic crust subducts, and then the two plates run into each other, and neither one is going to sink because they're too buoyant, they're too thick. And so they just fold and pile up. So the edges get intensely deformed and you get fold mountain ranges. And this is how continents can increase in size, by basically suturing on bits of land that was elsewhere. So if you look at the coasts of the US, there are bits of things that used to be you look at the East Coast, You get the Appalachians, which were where before Pangea formed, like the mountain, like the Appalachians. Then you have bits of, which was like a microcontinent that got sutured on, and some volcanic island arcs, and then the edge of Africa, and then it split apart again. So that you can do that. Look at that on the East Coast. You can do something similar with the West Coast. There's whole bunches of different things that have gotten glommed on to the West Coast of the U.S. as well. So that's how continents get bigger. And this is happening right now with the Himalayas. The Himalayas went along, slammed the Indian subcontinent, slammed into Asia. The Himalayas piled up, creating the Tibetan Plateau and such. And the tops of the Himalayas have got the marine sedimentary rock that was scraped off the bottom in between the subcontinent and Asia when they were coming together. So the tops of the Himalayas are covered with marine fossils. So continents increase in size, and they can basically glue themselves together along fold mountain systems. So here is a video about the formation of the Himalayas. We have the subcontinent coming in to the main continent of Eurasia, piling up, forming mountain systems with everything piled on top of the material from the ocean gets scraped up and piled up there. And that's the youngest mountain range. So some examples of this, the Himalayas and the Alps are more recent ones of this sort of fold mountain range. Himalayas are the youngest fold mountain range on Earth at the moment. The Alps, I think, are a little older, and the Appalachians are an old example of this. Happened a long time ago, so they're worn down, very rounded. But the idea is basically continental crust slams into continental crust, and because it can't sink, everything just piles up. And lastly, we have transform boundaries. Transform boundaries are where two plates are sliding against each other side to side. So you don't get new crust formed by tearing apart. You don't get, things aren't slamming together. Nothing is created or destroyed. So in general, divergent boundaries make new crust. Convergent boundaries destroy old crust. Transform boundaries do neither, because they're where things are sliding across. So this is a region with shearing or transform motion, the side to side sliding. Crust is not destroyed or created along a transform boundary because neither subduction nor magma upwelling occur. But you do, because you have these big plates sliding against each other and they have friction, they'll stick. And when they unstick, you get earthquakes. So the periodic movements along these faults result in sudden energy release and repeated earthquakes. So these zones are seismically active. And the most famous of these is the San Andreas Fault in California. So this is a video about the San Andreas Fault in California between, the North American Plate and the Pacific Plate.
These giant gashes in the Earth are reminders of our planet's awesome power. They are fault lines, fractures in the Earth's crust where huge slabs of rock slowly grind past each other. Most faults we can't see, but here in California, the San Andreas Fault is visible at the surface.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with 1 foot on one tectonic plate and one on another. In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
The San Andreas Fault sits on the boundary between the North American and Pacific plates. It's called a strike-slip fault, a place where two plates collide and try to slip past each other. As these plates move or creep in different directions, sometimes they get stuck. The longer they stay stuck, the more tension builds and the bigger the eventual quake. In other places, the plates move smoothly past each other. These areas buckle as the Earth shifts. The changes are subtle. Roger Billam keeps track of these changes with his creep meter, a device that measures movement along the fault. A computer collects data every minute for a year. This jump in the graph tells him the Earth shifted about 5 millimeters in a couple of hours. A small shift like this can have huge consequences for us.
That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field, there aren't any people. But further north, this creep process and the things that are happening beneath the Earth are far more sinister.
The San Andreas Fault and its branches trigger more than 10,000 quakes a year. Sometimes the results are devastating. Just ask the people of Los Angeles or San Francisco. Over the last 2 decades, major quakes rocked both of these cities. Life goes on, but the risk remains. In an area this active, the next violent tremor could happen at any time.
So this is a summary of the different types of plate boundaries. We have divergent boundaries, which make new crust, convergent boundaries, which destroy crust, destroy oceanic lithosphere. Divergent boundaries make new oceanic lithosphere, convergent destroy it, and transform boundaries where crust is neither created nor destroyed. So going apart makes new crust, coming together destroys old crust and can make volcanoes and such, and transform boundaries give you earthquakes. So volcanoes, as the term volcano could refer to both any place where a vent where hot molten material escapes, or the mountain that gets created by that hot molten material. So we use the term volcano for both anywhere liquid rock is coming out of the ground and the structures that are made from that liquid rock. And though the specific occurrence of volcanic activity is usually unpredictable, like we don't know when a volcano is going to go off. The location of eruptions and possible eruptions are pretty well known. Basically, we can figure out, yeah, this is a place where you might have a volcanic eruption, but we can't tell whether, and we might even be able to tell it's likely to have a volcanic eruption sometime soonish, but we can't tell, like, is it going to have an eruption this week, this year, that kind of thing. That's much harder to predict. So the most common places for volcanism are along plate boundaries. So along plate boundaries, you get volcanism. At divergent boundaries, you're splitting apart. So magma wells up. At convergent boundaries, one plate is sinking under the other. So you get melting rock and the stuff rising up. So here is, this is Japan and other places. You can see all around the Pacific Ocean, there's a lot of these volcanoes. But there are volcanoes at places that aren't at plate boundaries. This is Hawaii. Hawaii's smack in the middle of the Pacific Plate. What's going on there is that there is a magma hotspot, just an upwelling of hot magma underneath the middle of the plate. And that's causing the volcanoes of Hawaii. And there's a few other places like that around. So not all of them have active volcanoes, but like Yellowstone National Park is also sitting on a hotspot like that. So when two plates collide, one plate usually gets subducted into the other, and during this subduction process, the rock just above the subducting plate margin melts, resulting in the molten rock rising to the surface to form volcanic islands or mountains. So this is why there's all these volcanic islands around the Pacific Ocean and other places like that. So, you know, all of Japan, the Aleutian Islands in Alaska, things like that. And that ring around the Pacific is known as the Ring of Fire because of all the volcanic activity. And most of it is underwater. So here's a video about that.
There's another world beneath the ocean's surface. Come join us as we explore the depths below. Orange and red flashes in the pitch black. Lava oozes from the cracks and rolls across the ocean floor. Earthquakes rumble and roar as tectonic plates grate against each other. We're at the rim of the Pacific Basin. Because it is one of the most geologically active places on Earth, scientists have nicknamed the area the Ring of Fire. The movement of tectonic plates has created a nearly continuous series of oceanic trenches and chains of volcanoes stretching for 25,000 miles. The Ring of Fire is home to hundreds of volcanoes, but most remain hidden far below the water's surface. In fact, 75% of all volcanic activity on the Earth happens in the ocean. But the effects of all this activity aren't felt only in the Pacific Basin. Earth's ocean and geology are global interconnected systems that can affect us all. Tsunamis can be generated by underwater earthquakes, volcanic eruptions, or landslides. And as we have seen, their impacts can be devastating. Undersea volcanoes produce chemicals and heat that affect the ocean environment. We need to better understand these natural inputs as we increasingly introduce our own with man-made pollutants. We've only recently begun to explore the hundreds of volcanoes rising from the ocean floor that make up the Ring of Fire. Over the last few decades, several expeditions to the Western Pacific Basin have been conducted. Using the latest mapping and robotic instruments, researchers have learned more about the geologic activity at these sites and the marine life that thrives on hydrothermal vent systems. But learning new things often leads to more questions, which means there's still a whole lot more left for us to discover. So join us as we continue to explore the depths below.
So here's an example of the way that the subduction of oceanic lithosphere forms volcanoes and can form a volcanic island arc, such as Japan. So here we have the Pacific Plate subducting under the Eurasian Plate, the edge of the Eurasian Plate. They're subducting. As it subducts, the Pacific Plate melts, magma rises and forms volcanoes, forming the island chain of Japan. So that is sort of roughly how we get volcanoes. Earthquakes are caused when the crust suddenly slides. It's a sudden release of energy due to a sudden movement of the Earth's crust or mantle, resulting from the release of stresses. So stress builds up between two plates along a fault line, and then eventually it overcomes friction and you get a sudden jerk. And the study of earthquakes is called seismology. And earthquakes cause the Earth's surface to vibrate and sometimes can result in very violent movements, depending on the amount of energy being released and how that energy gets transmitted. So, like, the danger from earthquakes depends on a lot of factors, like what the ground underneath you is made of and things like that. So earthquakes occur when rocks grind past each other at plate boundaries. And during this process, vibrations will radiate out in all directions from the source of the disturbance. And the major danger from earthquakes is not really the vibrations, but the fact that they cause human-made structures to collapse. And they cause damage to other human-made structures, which can lead to things like fires and destruction that way. So, you know, if you're in an earthquake out in the middle of a field, you'll be fine. Very rarely do earthquakes do things that can make you in trouble if you were just standing in an open field. But if you're in an earthquake in a building, you're potentially got problems. So most earthquakes are caused by movements of the lithospheric plates. There are other possible causes, but that's the primary cause. They can also result from explosive volcanic eruptions or human-caused explosions. There's some stuff that's happening with fracking. And movements of lithospheric plates generally causes faults in the crustal material. And a fault is just a crack in the rock where both sides have moved relative to each other. So it's a fracture in the rock where there has been visible movement of the two sides relative to each other. If there hasn't been movement, it's called a joint. So this is an example of a fault. You can see here these layers of rocks, and you can see how this side has gone up and this side has gone down. Now, earthquakes are most likely to occur along plate boundaries because stresses build up on the rock formations of the adjacent plates as they move relative to each other. And since rock possesses elastic properties, it can bend. Energy gets stored up until the stresses involved overcome the friction between the two plates, and then there's a sudden release of all that stored energy. The rocks along the fault suddenly move, the energy gets released, and an earthquake occurs. And as that energy is released, it causes vibrations in the rock that spread out from the point of release. And earthquake occurrence closely follows the same distribution as volcanoes. You know, it happens along plate boundaries primarily, with some, you know, exceptions, like you can see here in the middle of the North American plate. And generally, after a major earthquake, you'll get aftershocks as things settle back into a more stable configuration that can send out more shocks. You know, the rocks are continuing to adjust to their new positions. Now, transform plate boundaries are where some of the world's largest continuous faults are. These transform faults, and the San Andreas Fault in California is the transform fault that lies between the Pacific and North American fault plates, and is probably the most famous of these. But there are plenty of other ones, like there's one in Haiti, and other places as well. The San Andreas Fault in California is the master fault of an intricate fault zone that runs across the coastal area of South and Central California. That fault system hits land in southern Oregon and exits in Mexico. The split, the Gulf of California, it continues to run through the if it's the Gulf of California, it'd be, you know, the strip of ocean between Baja California and the rest of Mexico. And lots of earthquakes have occurred along this fault, and because there's a decent number of large cities and such along it, it, you know, is famous. In 1906, a major earthquake occurred in the San Francisco area, resulting in hundreds of lives lost and millions of dollars of damage. In 1989, a major earthquake in the area again caused severe bridge building and highway damage. And there's nothing we can really do to control this fault line. All you can do is design your structures so that they're able to survive earthquakes. You can't prevent earthquakes, you just need to weather them, essentially. So as the San Andreas Fault continues to move, eventually, in about 10 million years, Los Angeles will move far enough north to be adjacent with San Francisco. Because, you know, this whole area is moving north compared to the North American plate. And here's the Baja California, and the fault line, you know, penetrates into this area. And at the point of initial movement or energy release along the fault is called the point where the earthquake starts underground is called the focus. And that's generally located underground. And it can be from a few miles deep to several hundred miles deep. Now, the term that you'll hear most commonly is the epicenter. The epicenter is the point on the ground immediately above the focus. That's the point where earthquake waves first hit the surface and where earthquake waves, if you're only looking at the surface, appear to come from. So this is the surface position that receives the greatest impact from the earthquake. It's the first hit, it's going to get the biggest waves because they're spreading out from that focus, and that energy gets spread out over larger and larger areas. So it's strongest at the epicenter and weaker as you go further away. And the way you can locate the epicenter is by measuring the waves at several locations. Oops. So these waves travel outwards, they travel at a certain speed, and there are two types we mentioned earlier. There are S waves and P waves. And P waves are faster than S waves. So if you measure the difference in time between the S waves and the P waves, you can figure out how far away you are from the epicenter. If you do that at several locations, you can work out where the epicenter is via triangulation. You need 3.
Okay, so let's take a look at how to locate the epicenter of an earthquake using the triangulation method. All right, so here is a map of the world, and we're going to zoom in on a particular region. We'll look at North America, and let's imagine that there was an earthquake somewhere in North America. Well, the question arises, where was the epicenter of that earthquake? Now, we may be able to get a general idea of where the epicenter was based on looking at the severity of damage, eyewitness reports, etc. But if you want to pinpoint the actual location of the epicenter, you have to do some calculating. And so let's look at how we're going to do that. First off, in order to pinpoint the epicenter, you need a minimum of 3 seismic stations. So let's pop a few of these seismic stations on the map. Let's say we have one here in California, one up here in Canada, and one down south here, labeled 1, 2, and 3. Now, these are locations where we have seismometers actively monitoring the shaking in the Earth's crust. Of course, we have seismic stations all over the world. In order to use this triangulation method, we need at least 3 of these, or data from 3 of them. So, step 1 is going to be to take the data, the seismograms from each of these stations, and determine each of their epicenter distances. That is to say, I want to know how far point 1 is from the earthquake, how far point 2 is from the earthquake, and how far point 3 is from the earthquake. And this is fairly easily accomplished. You would simply find out the difference in arrival times for the P waves and S waves, and then use a travel time graph to calculate the distances. So let's say you have done that and you have established that seismic station 1 is approximately 700 kilometers from the earthquake. So something like this. But the problem is, we don't know if it's 700 kilometers in this direction, in this direction, in this direction. We don't know. It could be 700 kilometers in any direction. So what we can do is draw a circle around point 1 with a radius of 700 kilometers. And now we know that the epicenter is somewhere on that circle, somewhere on that line. But again, that's not good enough because we want to pinpoint the location. So let's turn our attention to location 2. And say we did our math and we found that location 2 is 3,000 kilometers from the epicenter. Now again, it could be 3,000 kilometers in any direction. So we will draw a circle around point 2 with a radius of 3,000 kilometers. Now notice something. If you did this properly, your circles should intersect, most likely in 2 places. And what that means is that the earthquake had to happen either here at this intersection or here at this intersection. But again, that's not good enough because we want to know exactly where the epicenter was, which leads us to station 3. We take our seismogram, we do our math, and we determine that station 3 is approximately 3,500 kilometers from the epicenter. So, again, it could be in any direction, so we take a drawing compass and we draw our circle with radius 3,500 kilometers. Now, if this works out properly, all 3 circles should intersect in one single point. And that point is your epicenter, shown by the pink star. This is what we call the triangulation method for locating the earthquake epicenter.
And this sort of triangulation method gets used in a lot of other things. It's actually how GPS works. You get signals from, I think you need 4 satellites to properly locate yourself on the Earth. And by comparing the delay of the signal from those 4 satellites, basically, you can figure out how far away you are from them and locate yourself. I think you need 4 to figure out where you're on the surface, and a 5th one lets you figure out altitude. You need an extra one because of the way they're figuring out distance. For satellites, you only need 3 there because they have an easier way to get distance. And then you need another one to get a 3rd dimension, basically. But it's the same idea. You're basically just drawing spheres instead of circles for 3D. So for an earthquake, this is the focus underground. The point immediately above it is the epicenter and the fault line. So the fault line may not be cutting vertically through the earth. It may be at an angle. So the epicenter is not always going to sit directly on the fault line. And when an earthquake occurs, the energy gets released from the focus. It propagates outwards in all directions as seismic waves. These can be measured with a seismograph that monitors and measures these seismic waves. And the greater the energy released by the quake, the greater the amplitude of these waves, the height of the lines on the seismograph, and thus the higher it rates on the Richter scale. So the Richter scale is a scale that's based on the amplitude of seismic waves, at least originally. It's been modified a little since then, because it turns out the original Richter scale doesn't work so well for very big earthquakes. But basically how a seismograph works is that you have like a measuring, like photographic paper or something, a measuring spool, it's anchored to the rock, the frame is anchored to the rock, but your source that's doing the drawing is decoupled. There's like a spring or something that lets it move up and down when the ground moves up, and it lets it stay in place when the ground moves up and down, moving this, and thus you get a record of the motion of the earth. And the severity of the earthquakes are measured on 2 common scales. The Richter scale measures how much the earth moves. And the modified Mercalli scale measures damage. So the Richter scale is the modern version, the modified magnitude scale, which is what it's called, the modern version of the Richter scale, measures the amount of absolute energy released during a quake by calculating the seismic wave energy at a standard distance. Originally, it had to do with the amplitude, but it turns out for really big earthquakes, the amplitude kind of caps off. You still have lots of energy, it just doesn't make your waves any higher necessarily. And so there were some complications there. But the general structure was that the original Richter scale was that for every 1 up on the Richter scale, you had 10 times the amplitude. The modified Mercalli scale describes the results of an earthquake in terms of felt and observed effects. So the Mercalli scale is about damage. What happens? And so 2 earthquakes with the same value on the Richter scale can have very different experiences with the Mercalli scale, because this can be affected a lot more by things like what your ground is made of and things like that. So the Richter scale was developed in 1935 by Charles Richter of Caltech. This is the most common form of earthquake measurement. When people talk about earthquake in numbers, that's what they're using. It correlates the largest seismogram peak during a given quake to the amount of energy released by the quake. Again, the more modern version realized that that sort of saturates, so there's some corrections made at the high end. But it only affects really big earthquakes. And the Richter scale gives the earthquake's magnitude expressed in numbers. And for earthquakes that humans experience, those numbers are usually between 3 and 9. Below 3, you basically can't feel it. And earthquakes above 9 are terrifying and generally don't happen. One of the more entertaining videos on the XKCD What If channel on YouTube asks someone asked what would happen if there was a magnitude 15 earthquake on Earth. A magnitude 15 earthquake on Earth would literally destroy the Earth. It would tear it apart because it's so much more energy. The biggest earthquakes ever recorded are a little bit above 9. Part of this is that it's a logarithmic scale. So every time you go 1 up on the Richter scale, that represents a 10-fold increase in the size, the amplitude tracings. So a magnitude 4 earthquake, the ground is moving 10 times as much as a magnitude 3 earthquake at the biggest amplitude. It's moving 10 times higher. And because of this, it turns out each whole number increment represents a 31 or 32-fold increase. It's between 31 and 32. Increase in energy release. So an earthquake of magnitude 5 releases 31 times the energy of an earthquake of magnitude 4. And an earthquake of magnitude 6 actually releases, it says more than 900 times here. It's actually exactly 1,000 times more. It's 31 because it's the square root of 1,000. So an earthquake of magnitude 6 releases 1,000 times more energy than an earthquake of magnitude 4. Now, one big drawback of the Richter scale is that the magnitude of an earthquake doesn't really give good indication of the damage it can cause, because earthquake damage depends on a lot of other factors. The magnitude of the earthquake tells you how big the vibrations are, but the effects of those vibrations depend on what they're running into. So things like where the focus is located, the geologic rock types things are built on, the population density, how things are constructed. That determines the damage. The relatively moderate quakes in areas with high populations and with poor construction techniques can cause horrific property damage and loss of life. Considerable property damage and loss of life, while more severe quakes in more sparsely populated areas could cause very little damage. So this is part of why those earthquakes in Haiti were so awful, is because construction there. It was hitting like very poorly constructed shanty towns. All the vegetation had been removed, so there were lots of landslides, from these earthquakes. It was really horribly destructive. Well, if you have a massive earthquake where nobody lives, it doesn't really do that much. So, if the magnitude of an earthquake is less than 3.5, you generally don't even feel it. It gets recorded, but you don't feel it. Somewhere between 3.5 and 5.4, it can be felt, but it rarely causes damage. There are some hilarious videos out there of streamers getting hit by earthquakes that aren't huge. But and then under 6, you get at most slight damage to well-designed buildings, and it can cause major damage to poorly constructed buildings over small regions. So, in this range, you can have issues with, your house shakes, stuff can fall down. That can be dangerous, but and then 6.1 to 6.9, these can be destructive in areas up to about 100 kilometers from the epicenter. 7 to 7.9, these are major earthquakes that can cause serious damage over larger areas. And 8 or greater, that's a great earthquake. These cause serious damage in areas several 100 kilometers across. And there's only been a handful of earthquakes that are greater than that. So damage from earthquakes may be directly related to the vibrational tremors, or it may result from a number of secondary effects. The biggest killer in earthquakes is fire. Or at least it was for a long time. Because it damages things like gas lines, and fires can start. And it also damages water lines, so firefighting is impeded. So landslides are commonly triggered by earthquakes. So a lot of the damage in the 1964 Alaskan quake was due to a series of small landslides. The 1964 Alaskan quake was the biggest earthquake in North America. And some of those landslides were crazy. They had whole neighborhoods slumped down and tilted over like 40 degrees. Fires initiated by the initial tremors are very difficult to fight due to broken water lines. The U.S. government, FEMA, has literature available on earthquake preparedness. So places with lots of earthquakes like Japan has developed systems that, to help prevent damage from earthquakes, will cut off water and gas lines as soon as earthquakes start. So if those lines break, they're not going to cause any real additional damage. And one of the serious issues with earthquakes is liquefaction, where due to vibration, soil can basically turn into quicksand and flood. So you can get sinkholes and buildings tilting over and all kinds of crazy stuff. So here are some dramatic examples of liquefaction in the Christchurch earthquake from 2011. Tracks to the ground. You get loss of utilities. It's called car sinking into the dirt.
We're just coming to check a couple of our family members, see if they're all right and got food and water.
Whole new level of hiding space. Sinkholes, fire lines falling over because
we're really quite stranded, really. Roads are bad, obviously.
Can you get my sister on TV?
We've just come from Brisbane.
You gotta give up on that.
And I'm not sure which is the worst.
We're not really sure where we're going to go from here.
If it rock and rolls again tonight, well, we'll think about leaving.
Do what you always do. to in Canterbury, which is reach out to one another, be good neighbours, talk to one another, help each other out, do the very best you can. We will come through this.
Today, all New Zealanders grieve for you, Christchurch. Though your buildings are broken, your streets are watched, and your hearts are aching, your spirit will overcome.
And now, submarine earthquakes also happen. You have earthquakes in the ocean. The biggest effect from submarine earthquakes is generally not actual vibrational damage from the earthquake. The seismic waves aren't the problem. The problem is these submarine earthquakes can create tsunamis. And sometimes these earthquakes are truly enormous and create these massive, highly destructive tsunamis, where it's water waves caused by the motion of the crust underneath. And tsunamis are not only caused by earthquakes, they can be caused by landslides, volcanic eruptions, things like that. But they're these really big waves. And if a tsunami is caused, there are systems out there that track tsunamis to give advance warning. But if a tsunami is caused close to you, there's not much warning. So the recent Indonesian tsunami was highly destructive. But it is 9:45, so we are out of time for today. Let me see. Oh, okay. I had like one more slide. I'll just move that to the beginning of the lecture next time.